Okay, let's start talking about finite sets. So we'll start with definition 120. And before I write it down, let's just remind ourselves what the actual numbers are, what the natural numbers are actually defined to be. So we have 0 we defined to be the empty set, right? Then we said 1 will be the next of 0, which is, well, it's singleton 0 union singleton 0. Right? So that was just singleton 0. Because the empty set union singleton 0. And then 2 is the next of 1 is 1 union singleton 1 is, well, 1 is the set singleton 0, and when I union singleton 0 and singleton 1, I get this. And hopefully you're seeing that each time, so like 3 is going to be 2 union singleton 2. So take the previous list, consists of 0 and 1, and then throw in the entire list itself, which has the name 2. So you get 0, 1, 2. What's 4 going to be? 0, 1, 2, which is the previous list, but then throw in the list itself, which is called 3. So that's how next works. It takes a list of natural numbers, if you apply next to a natural number, and it takes that list of natural numbers that are its elements, and then it adds to that list the natural number itself. It adds the list itself as an item into the list. All right, well, the bottom line is, it seems that 0 is a set that has 0 elements, whatever that means. We're actually about to define what it means for a set to have n elements, for a number n. But just staring at it, 0 seems to be a set that has 0 elements. 1 has 1 element, 2 has 2 elements, 3 has 3 elements. So that's pretty convenient. You know, we didn't have to define the natural numbers so that this happens, but it's convenient that it did happen. So the following definition is sensible then. Let's see. First I'll define what it means to say a set has n elements. A has n elements. So this phrase, I'm defining this phrase, it's going to be a mathematical proposition, which means n is a natural number, first of all, and A has the same cardinality as n. Let me make sure I'm writing things in the correct order, that they show up in the notes. Right. Yeah, so if someone says A has 0 elements, for example, if I say A has 0 elements, then what does that mean? That means 0 is a natural number. Well, that's true, that 0 is a natural number, so I don't need to say that. What it really means is A is in bijection with 0. Meaning, there exists a bijection between A and 0. 0 is the empty set. It should be possible to prove that there can only exist a bijection between a set and the empty set if the set itself is empty. So you should be able to prove, so this will be one of your homework problems, you should be able to prove that this happens if and only if A itself is the empty set. So that's nice to know that our definition works, at least when you put in n equals 0, it seems to do the right thing. Having 0 elements is the same as being empty. All right, just to keep trying things, what about having 1 element? So if you have 1 element, then that's just the same as saying that there exists a bijection between u and 1. Now, that's not the same as saying A, equals 1. That's not the same thing. To say that there's a bijection between A and 1 is to say that there exists a function from A to 1 which is bijective. Let's see if we can prove that this think this will be a good exercise to do on the chalkboard right now. Let's see if we can prove that having one element means that you're a singleton, that you're a set consisting of exactly one thing, that you can be expressed as singleton sum. Let's prove that. So there's more to this definition coming up, but first, let's just prove this claim. A has one element. It's really an if and only if, but let me just do one direction. Implies A is a singleton. All right, so proof. Assume A has one element. How do I use this fact that A has one element? I have no choice but to use the definition. That just means A is in bijection with 1. So then, A has the same cardinality as 1. Sometimes people say is in bijection with. A is in bijection with 1. That doesn't mean I'm talking about any specific bijection. I'm just saying there exists a bijection from A to 1. Okay. How do I make use of this? Well, I know there exists a bijection, so I can get one. Get or let f from A to 1 such that f is a bijection. Now, I really wish that f mapped 1 to A rather than A to 1. And I could just as well have f maps 1 to A, since this relation, wiggly equals, is symmetric. So let me reference the correct thing here. Theorem 115.2. So 1 wiggly equals A by 115.2. All right, so then we can get f from 1 to A such that f is a bijection. That does not mean 1 equals A, right? Just having a bijection doesn't mean these are equal. Now, 1, I can rewrite 1. 1 is singleton 0, right? So that means, since 1 is the domain of this function, 0, let's write it like this, 0 is in the next of 0, which is 1, which is the domain of f. So just notice that. So that means I can talk about f of 0. So f of 0 is the thing. Now what should I do with it? Well, my goal is to prove that A is a singleton, right? Let's think in terms of diagrams for a moment. Here's the set 1. There's exactly one thing in there. It's called 0. Here's the set A. I'm trying to show that A is singleton x for some x. I know that f sends 0 over to something called f of 0. F of 0 is something in here, right? So I know that f of 0 is an element of A. So how can I prove that A is a singleton? Well, probably I'm going to prove that A is singleton of f of 0. So let that be the next claim, that A is the singleton set consisting of only f of 0. So let's call this our subclaim. A is that singleton set. Okay, so here's the proof of the subclaim then. Let's do 2 inclusions. Let me fit that in, one inclusion here and one inclusion here. So let's suppose that something is I think this one is easier. Let's get the easy one out of the way first. So let Z be in the right side, singleton f of 0. Then, by definition of singleton, z equals f of 0. Then is z in A? Well, I think so, but how do I know? What exact previous state assertion that I've made gives me that? It's the fact that f maps 1. Let me write this as 1. To make it look similar. It's the fact that f maps 1 to A. So A is a possible codomain, meaning A contains the range of f. And if I do f of something in the domain, if I evaluate f somewhere in the domain, I do get something in the range of f. So since z is f of 0, z is in the range of f, which is a subset of A. Thus, z is in A. Okay, so much for that inclusion. Now for the other inclusion, let z be in A, and then our goal is to prove that z is in this singleton. Probably the only way we can do that is to prove that z equals f of 0. Okay, well, let's draw a picture. So this is kind of the current situation. I've got f from 1 to A, and here I've got 0, and here I've got a point called f of 0, which is where f sends the point 0. And I've got z in A. So what if z were something different? Why couldn't it be something different? I'd like to show that z is f of 0. So why couldn't z be something different? If I have two dots on this right side, f of 0 and z here, what's wrong with this picture? There's some fact somewhere on the board that this contradicts, that this picture would contradict. One fact that we haven't used is that f is a bijection. So if z were different from f of 0, then it looks like f would not be a surjection. Because there's only one dot here. We know the set 1. That's a familiar set. It only consists of 0. There's only one dot here. And we know that dot goes to whatever f of 0 is. So if there's a second dot called z, then that dot doesn't have anything connecting to it. That contradicts the surjectivity of f. So somehow surjectivity is going to be the reason that z must be f of 0, that these dots have to be the same. So that's a hint. That picture is a hint that we need to use surjectivity. So, okay, what does surjectivity give us? It tells us that everything in the codomain is in the range. So z is in the codomain. Then, since f is surjective, z is in the range of f. That means z is f of something. So then we can get, let's say get, something, let's call it x, in the domain of f, which is 1, such that f of x is z. That's what it means to say z is in the range of f. Z is f of something. So let's get that something, call it x. Now if x is in 1, well 1 is singleton 0, so x must be 0, right? Since x is in 1, which is singleton 0, x is just 0. Thus, z is f of 0 is in singleton f of 0. That's what we needed. So there's the two inclusions. All right, so we have proven this implication, that if A has one element, then A is a singleton. That's good. What about the other implication? Let's just do that too. Before I erase this, so one comment. Here I proved that A is a singleton by coming up with a potential singleton that could be A and then proving that that singleton does equal A. But there's a kind of more natural way to prove that A is a singleton, which is just to prove that A has a unique element. And if you're going to do it that way, then you can by using one of our earlier things. Theorem 25. Theorem 25 says a set is a singleton if and only if it has a unique element. Okay, so this was a little bit less efficient. I didn't use Theorem 25. Now, let's try to prove the converse. So it becomes an if and only if. So let's prove this way. If A is a singleton, then A has one element. So assume A is a singleton. Then, what can I get out of that? Is a singleton. That's something we've defined before. It means there exists some x such that A is singleton x. So then we can get x such that A is the singleton of x. Okay, now my goal is to prove that A has one element. So what am I trying to prove? I'm trying to prove that 1 is a natural number. Okay, I don't need to do that. And that A has the same cardinality as 1. So I'm trying to find a bijection from A to 1, or from 1 to A, either way. Let's do a bijection from A to 1. So how do I find a bijection from A to 1? If I want to show there exists a bijection, I have to find one. How do I find one? Well, either I'm going to reference some other theorem somewhere that tells me there exists a bijection that does what I want, and I'll use that theorem and its existence statement to get a bijection here. But I'm not in that situation. I don't know of any other theorems that tell me there's a bijection that does what I want. So how do I get one? How do I find a bijection? I have to construct one. Okay, so this is something that I think it's strange we haven't done very frequently in this course, is building a function, constructing a function that does things you need to demonstrate things. So here we have to do it. We have to build a function from A to 1 that is bijective. Okay, well, a function is a set of pairs, so maybe I can just list all the pairs I want. Luckily, there's only finitely many pairs that I'm going to need. If there were infinitely many pairs, then I might use that kind of notation. But here, I can just list the pairs that I need. What do I want f to do? So maybe just look at the picture. Here's A. It has one thing in it, which is x. And here's 1. It has one thing in it, which is 0. And what do I want f to do? I just want it to send the point x to the point 0, and to do nothing else. So, there. So f is just that. F itself is a singleton set. Then, f maps singleton x to singleton 0. And f is bijective. Okay, so these are things that you would have to prove. There are 3 statements here. F is a function, the domain of f is this, the range of f is a subset of this, and f is injective, and f is surjective. So 3 things to prove here, 2 things to prove here. And let me stop here and say, you can probably fill in the rest here. All right, and here's the rest of definition 120. So we've already defined A has n elements if and only if n is a natural number, and A has the same cardinality as n, meaning there exists a bijection between A and n. We say A is finite if this happens for some n. So a finite set is a set which has n elements for some natural number n. In other words, a finite set is a set for which there exists a natural number and a bijection from the set to that natural number. And an infinite set is just a set that is not finite.